Answer key should be posted on Moodle. I think I did that. Feel like I remember doing that over the weekend. With the way the homework's working, if your homework grade looks like it's pulling things down, but you've made the option not to count the homework grade, just average your exam grades. It'll give you a much better idea of where your current grade stands. So if you have any questions, of course, feel free to reach out about that. Happy to go over that. And if you've got questions as you go over the exam and want to ask questions about things, I'm happy to go over that as well. And along those lines, are there any questions before we get going? All right, well, let's go on to the next section then. So we've talked about how we can determine if a set of vectors is linearly independent. We're going to also talk about how a set of vectors spans a vector space, how we can tell that. Both of those involve doing what? What do you do to check the set of vectors is linearly independent or span? In both cases, what do you do? All right, you make a matrix of overhead, right? That's the idea. So you look for the pivots. The pivots tell you whether or not you've got a linearly independent set or a spanning set. If it does both, what do we call that again? Basis, right? All right, so we've had all of those discussions. We're going to continue those discussions for a few special types of spaces that we can create from a matrix. So rather than taking our vectors and creating a matrix, let's say we already have a matrix given to us. So we've got an M by N matrix. So we've got M rows and N columns. These are going to be, we're going to think about the columns and the rows being vectors, okay? So we're going to, rather than taking vectors and creating a matrix, we're going to go the other way. Take a matrix and create some vectors, okay? Since all of our entries that we're going to be putting on our matrices are real numbers, all of our vectors that we'll be talking about will be real vectors, right? They'll be vectors of R, some R whatever power, right? So let's think about where those vectors might live. If I take a row of an M by N matrix, if I take a row, how many components would that vector have? M or N? N, right? Because you're going to cross the columns, right? So your rows can be thought of as vectors in Rn. Your columns can be thought about as the vectors in Rm. Okay, good. So that's exactly what we're going to talk about when we're forming these spaces. So when we talk about the row space of A, this is going to be the span. Yes. M represents going 1, 2, 3, 4 down to M, right? So if I take the column, it's going to have M components. Yeah. So your row space is going to be the span of the rows of A. And this will be, since it's a span, remember span is the set of all linear combinations. That's automatically going to be a subspace. Okay, so this will be a subspace. Bless you. Bless you again. That'll be a subspace of Rn, because we said as you go across the rows, I'm sorry, did I not give you one? My apologies. Oh, I'm sorry. My apologies, I thought I got you one. As you go across the columns, right, the rows, you're going to across the columns, there'll be N components there, right? So when you do the row space of A, it'll be a subspace of Rn. The column space is defined similarly. I never can say that word right. This is the span of the columns of A. Oops. This will be a subspace of Rm. All right. Notation. We'll use row of A to denote the row space. and we'll use COL of A to denote the column space. One more special space we refer to as the null space. When you hear the word null, what do you think of? A zero, right? When they hear the word null, I think zero, right? So this is actually a solution space. This is the set of solutions to the equation AX equals 0. It's the set of solutions to the associated homogeneous system. We've already done that stuff, right? Okay. Now, if it's going to be a solution to this homogeneous system, notice I got to make sure my matrix multiplication is correctly defined, right? Where does X live? What kind of vector is it going to be? What Euclidean space does that live in? Yeah, two guesses. What are they? What are your two natural guesses in this case? Rn. It's Rn or Rm. Which is it? Okay, so I got to make sure my matrix multiplication is defined. If A is m by n, X needs to be n by 1, right? So it has to be a vector in Rn, right? So this will end up being a subspace of Rn. Okay. So two of these spaces that we're doing or looking at here are subspaces of Rn, and one is a subspace of Rm. Okay. All right. Pardon me. All right. So the rank is an idea of dimension, and we talked about how to do dimension before the exam. You had a question about dimension on the exam, right? Remember how you find the dimension. By definition, dimension is number of elements in a basis, right? Right? That's by definition, correct? On one of the problems you had on the exam, I gave you a subspace W and asked you to find the dimension, right? If I take a spanning set and reduce it, I make my matrix and I row reduce. What do I look for to go back and pick out the basis? What do I look for in the reduced row echelon form? The pivots, right? The pivots correspond back to the basis, right? So each pivot is going to give us a basis vector, right? So when we talk about the rank of a matrix, that's exactly what we're looking for, is those pivots, okay? The rank of a matrix is the number of pivots in the reduced row echelon form of A. Oh, I forgot to give a notation for null space. I'll write it down here in a second. So when you row reduce and get those pivots, if you count the number of pivots, that's going to give you the rank of the matrix. Like I said, I forgot the notation back up here. You see NULL of A. That's the null space notation. Rank is pretty easy. It's rank of A. It's a pretty easy notation for that one. Okay. Now notice in the first three, those notations are referring to a space. Rank is referring to a number, just like dimension refers to a number. Okay. All right. So in particular, if I think about how this relates to the column space, remember we said if we wanted to find a basis for find a basis from a set of vectors, you put those vectors in as columns and row reduce, and then go back and grab the columns that corresponded to the pivots, right? Okay. Well, then the number of pivots is going to correspond to the dimension of that space, right? So this rank turns out to be the same thing as the dimension of the column space of the matrix. the rank is going to equal that dimension of the column space. And I think I have a summary of this later too, but we'll go ahead and write it down now. Okay. We're going to come back to this idea here in a minute with respect to the row space. But right now, we can think about this in particular for column space, right? Because that's exactly how we went and formed our basis given a set of vectors, right? You put the vectors in a columns as a matrix, you row reduce, and you find the pivots, and you go back and grab those columns, right? If the column space is the span of the columns, then the span of the columns will just be those two, how many ever columns you get in the reduced row echelon, or that correspond to pivots in the reduced row echelon form. Nullity, well, if the rank is giving us dimension of the column space, or if rank is counting the number of pivots, what do you think nullity might be counting? Number of free variables. That's exactly right. So the nullity of A is the number of free variables, or the number of pivot-less columns, in the reduced row echelon form of A. Forgot an R there. No super fancy notation. If I want nullity of A, I actually write out nullity of A. You really want to abbreviate it as null, but we're already using that for a different thing. So just stuck writing the whole word. Number of pivots again, number of free variables again corresponds to the dimension of this solution space, right? I drop stuff. Corresponds to the dimension of the solution space here, right? So the dimension of your the nullity of the matrix will be the dimension of the null space of A. And we're going to come back to a connection between these two numbers here in a little bit. But all right, so these are just some definitions, and we'll talk about how we find bases for this here in a minute. But these are just the definitions for what we have for these different things. Yes? The first three are spaces. They're subspaces, yeah. They're sets of linear combinations. All right. So let's talk a little bit about importance of null space and column space. And we're going to talk about this in the context of systems of equations. So first, let's look at the consistency of a particular system of linear equations, or a particular matrix equation, if you will, in this case. What does it mean for a system to be consistent again? What does consistent mean? Like consistent versus inconsistent. What does consistent mean? Okay, so in particular, what does it mean as far as being able to solve this? There is at least one solution, but there might be infinitely many, right? That's what consistent means, right? We can actually find a solution. All right, so let's think if we have a solution here. Pardon me. If we have a solution here, what has to be true about, well, in particular, when we get a solution, what has to be true, we know what that means. If we plug in the vector here, we get the answer. But let's just talk about what this looks like if I multiply this out, okay? So if I take a matrix A and multiply it by a vector X, let's think about what happens. I can think about my X as being X1, X2, down to X M N here. That's right. So I'm doing an M by N matrix. When I multiply, we certainly do rows by columns, right? Right? We take the row and match it with the column. But everything in this first column here say I call it C1 this way, what does that get multiplied by? The x1, right? That C1 will get multiplied just by the x1, right? And the C2 gets multiplied by the x2, right? And so on down the line. So we take the x1 and multiply it by that C1 vector, right? We agree with that? Okay. Notice that what would we do next? We take whatever, say we want to do the first row. If I do the first row, I take C1 times x1, I take C2 times x2. What do I do with those two answers? Add them, right? So this will be a plus x2 C2, and then all the way down to xn cn, right? In terms of the columns, sorry, let me say it a different way. In terms of the column vectors, what kind of a thing do we call this? If I take a constant times the first vector plus a constant times the second vector and so on down the line, what do I call this type of thing? A linear combination. The set of all linear combinations of a set of vectors is called the span of the vectors, right? So this is a linear combination of the column vectors, or it's in the span of the columns. That means it's in the column space, right? Okay. No matter what I multiply by, right? Anytime I take a matrix and multiply it times any vector, whatever the vector happens to be, it's in the column space, right? Okay. If this is going to be a solution, it better equal to b, right? If this x, whatever this x happens to be, is going to be a solution, when you plug it into this equation, I better get b out, right? Right? So that means my b better be able to be written as a linear combination of the columns, or b is in the column space of A. Okay? Right. So just to write that down in words, if x is a solution, then ax is equal to the b, or b is equal to x1 c1 plus x2 c2, whoops, plus xn cn, which means that b is in the column space of A. In other words, this system is going to be consistent if and only if, I forgot the word and only if B is in the column space of A. Okay. So the column space of a matrix is tied to when a system is consistent, when that matrix is used as a coefficient matrix. Okay. Whatever's on the end, whatever you're putting on the equal sign, must be in the column space of A, or is expressible as a linear combination of the columns. Okay? And that's again just because of the way we might do our matrix multiplication. Why do we care about null space? Well, that's on the next page. Pardon me. If we have what we refer to this as one particular solution to a system of equations, What the theorem says is that you can write every single solution to that system as the particular solution plus something with the associated homogeneous solution. We talked about this a little bit before. Okay? We'll come back. We'll do this proof in a second, but let me give you a specific example of why this is important in differential equations. Okay? So here, this is a pretty typical way to solve something in differential equations, by the way. All right, here's a differential equation. This is something you could actually solve in Calc 1. This is not a hard differential equation to solve. Okay, especially if I get rid of the e to the x and make it a 0. If I make the associated homogeneous equation and write this down as y prime minus y equals 0, that's the associated homogeneous equation. Or rewrite it as y prime equals y. From a Calc 1 sense, what is that equation asking you? Think about a Calc 1 thing. I have a function. What has to be true about the function? It's the derivative is the same as the function. What function do you know does that? E to the x. As a matter of fact, any constant times e to the x works, right? So y equals a constant times e to the x is the general solution to the associated homogeneous equation. Okay. That's part of it, right? So, pardon me. What that means is, of course, if I put in this c e to the x in this equation, I don't get a solution to this one. However, when I put c e to the x in, I get 0, correct? Right? So if I could add something on here that would give me e to the x when I plug it in, then I could get a whole bunch of solutions, right? There's infinitely many of these, all right? If I can find just one function to where I plug it in and I get e to the x when I'm done, I could add it to these and get a whole boatload of solutions, right? So the idea in differential equations is now to try to find a particular solution, not infinitely many, but literally one solution to that equation. Any thoughts about how you might try to do that? I need to take the derivative and subtract off the function and get a single term. What kind of a thing that might you differentiate and subtract one thing off and get a single term when you're done? What kind of a thing when you differentiate it gives you two terms? And I might want to subtract something off and get a single term. What kind of an object gives you two terms when you differentiate it? Just from a Calc 1 perspective, if I take a certain thing and differentiate it and I get two things that pop out with a plus sign in the middle. So chain rule we chain together with what? Multiplication, right? I want a plus sign in the middle. A product rule, right? So I might want to look for a product of two things. Now, what do I want to end up at the end when I differentiate? I want to end up and subtract something off. I want to end up with an e to the x. What product, when you differentiate it, will give you a single e to the x when you're in one of the terms? X e to the x. So let's just try x e to the x. That derivative, I should say y equals. What do I get when I do y prime minus y? I get x e to the x plus e to the x, don't I, for the derivative? Minus x e to the x, and I get e to the x. So that is a solution, right? It works when I plug it in. So we found one solution. Now to get all of them, when I get all of the solutions to the original equation, we'll take the particular solution, the x e to the x, and add on the general solution to the homogeneous system. So this is what the theorem is saying. If I have one solution to the non-homogeneous system, if I have one solution to the non-homogeneous system, I can get all of the solutions by doing that one solution plus adding on a homogeneous solution. Okay? That's what this thing says. And like I said, it has applications in differential equations. I just showed you one. Okay. All right. So let's think about the proof of the theorem here. Okay. The proof of the theorem just says that if I have a particular solution, then I can write every single solution as that one particular plus something that's the solution to the associated homogeneous one, right? Okay. So let's let x sub p be a solution to, pardon me, ax equals b, and suppose that y is another solution. So now we have two solutions. They might be identical, but they have two solutions, right? It's entirely possible that I wrote the same solution twice. That's not a problem, okay? If I have two things, what might I do with those two things to convert now to a solution to the homogeneous system? What's on the right-hand side of the homogeneous system? 0, right? If I plug this one in and it gives me b, and I plug this one in and it gives me b, what might you do with these two solutions to create something that when you plug it in, you get 0? Subtract them, right? Just subtract them, correct? Okay? So then if I do a times y minus x sub p, what can I do with the a? Distribute it. Again, both of them are solutions to that system. So if I do a times y, what do you get out? B. When I do a times x sub p, you get b. So I get 0 when I'm done, right? So x sub, I'll call it x sub h. That difference is a solution to ax equals 0, right? Thus y equal to xp plus xh has the desired form. Let's again think about why this is important. And again, it's illustrated from what we did with the differential equation. If a homogeneous system has more than one solution, how many solutions does it have? Infinitely many, right? Right? If it has more than one, it has infinitely many, right? So if I find this thing has, sorry, where am I pointing? Here. This thing here has infinitely many solutions. We know how to find that, right? Especially in terms of matrix multiplication, don't we? We know how to find the solutions, the infinitely many solutions to the homogeneous system, right? We look for those free variables, right? Then to get the infinitely many solutions to the non-homogeneous system, rather than having to work for all of those particular solutions, I just need to find one. And then I can create all of them from the infinitely many in the homogeneous system, which is exactly what we did here, wasn't it? Found the infinitely many for the homogeneous, and then found one for the non-homogeneous, and wrote down all the solutions. Makes it a little bit easier, doesn't it? Let's see how this works with a specific example. I gave you a lot of room to write down a proof that wasn't very long. Let's do a specific example. All right. Here's a system of 4 equations and 6 unknowns. Rather than making you type all this into your calculator and row reduce it, which would have been really ugly, it's a lot of things to type, I went ahead and did it. So the left piece there is just your augmented matrix, and I don't have the vertical bar for your augmentation there, so I'll just draw it in there. And then when we're done, draw it here. All right? Okay. Is this system consistent? Start there. Yes. Yeah, I don't have any contradictions, right? So we have a consistent system, right? If these weren't here and these were zeros instead, what would your solution to the homogeneous system look like? Let's say I had zeros rather than -1, -5, and -2. What would your solutions to the homogeneous system look like? Okay, and I got an R, an S, and a T, right? Because I've got free variable in 2 and in 5 and in 6, right? So your X2 would be an R, your X5 would be an S, your X6 would be a T, right? Now again, I'm just doing AX equals 0, right? Okay. What would X1 be? Yep, a 2T. And minus 1S. And good, minus a 3R, right? Your X3 would be good. And your X4 would be good. And then we also talked about how we can split that up into pieces, right? Okay. I'm going to label it as X sub H, just to illustrate with what the previous theorem is. Your X sub H would be R times what? With a bunch of zeros, right? Okay. Your S would be good. And your T would be good. Everybody okay with those? Agree with that? Okay. Now, that would be our this would be our general solution to the associated homogeneous system, right? The next step is to find a particular solution to the non-homogeneous system, right? Well, no matter what homogeneous system you have, what's always a solution? Every single homogeneous system has what as a solution? The trivial solution, zeros, right? So if I think about the trivial solution, if I put 0 in for R, that would basically kill off that column, right? Because I wouldn't need to worry about that 3. If I put 0 in for S, it would kill off that column. And if I put it, I wish I had a third hand. If I had put in 0 for T, it would kill off that column. What matrix do you see left? Identity. Can you figure out what the particular solution would be? What does X1 have to equal? -1. What does X3 have to equal? And X4? -2. What would X2, X5, and X6 all equal in this case? 0. So what's your particular solution going to be? What was your X1? -1. What was X2? 0. X3? X4? And the other two zeros, right? That works. And you can check it, but that works, right? Because again, we said 0 is always a solution in a homogeneous system, so basically I can ignore, we'll make that one a 0, make that one a 0, and make that one a 0, right? Yeah? Okay. So now, according to the theorem, we can write all of our solutions as the particular solution. Oops, -0. That's not what I wanted to write. Particular solution plus the general homogeneous solution. And we've done this before earlier in the semester, didn't we? We called this parametric form, I believe, didn't we? Yeah. Okay. This is what we did earlier in the semester. We're just making it a little bit more conceptually precise, if you will. Well, back what we did earlier in the semester, what did we really do? We put in the -1 here, right? We put in the -5 here. We put in the -2 here, and then we split it off. Here we're just kind of just showing it a little bit more systematically of what we're doing, right? Find the homogeneous solution, then find the particular solution by making them all zeros. Which is, if you take differential equations, that's the way you do it. You find the homogeneous solution, and then find your particular. Yes? Mm-hmm. That's the homogeneous. XP is the non-homogeneous. No, I said for XP, put in 0 for the homogeneous solution. Use that specific homogeneous solution and see what's left. Basically, I said ignore that column, ignore that column, ignore that column. What do you see for a solution? That's what, so I made those all zeros. That's what I said for the XP. Basically, for the particular, I've already taken care of the homogeneous part. I need to figure out what actually gives me more information. Okay. I mean, that was what I did up here when I did the differential equation. I already found the homogeneous part. So I needed to concentrate on what do I need to plug in here to find the non-homogeneous part. It's the same kind of idea. I wouldn't want to use e to the x again because I already took care of the homogeneous part. So I need to do something else. All right. Let's go back to this example, but in the context of looking at what's happening when we do, pardon me, elementary row operations. Now, I literally wrote down the exact same matrix that I row reduced. However, in this particular case, I'm not interested in what's going on here. So I'm just going to scribble it out. I'm not really worried about what this part is. I want to worry about just the coefficient matrix and seeing what's going on. I want to talk about what does the null space of this matrix look like, and what does the row space look like, and what does the column space look like. That's what I'm interested in. Okay? So the questions are, what do elementary row operations do to the null space? Well, how do we find the null space? The null space, again, is the set of solutions to the homogeneous system. So what do you do to find the null space of the matrix? Not a trick question. What did we do to solve the homogeneous system? What did you do? Row reduce, right? When in doubt, if you have a matrix, what should you do to it? Row reduce it, right? Right? If you don't know what else to do, make a matrix and row reduce it. That's pretty much the kind of the theme of linear algebra, right? You don't know what else to do, make a matrix, row reduce it. Okay? All right. So that's exactly what we do. So what possible effect could elementary row operations have a null space? Does it change it at all? Do elementary row operations change it if what we do is perform elementary row operations to find it? No. Okay? So elementary row operations have absolutely no effect on the null space. It's literally what we use to find it, right? So nothing happens to the null space. Okay? What about the row space? Well, what are elementary row operations? What are your 3 elementary row operations again, just to remind? Row swap. Is that going to change your row space at all if I just flip around the order of the rows? No. What's another one? Yeah, multiply by a constant, right? So I just make the vector how many ever times is big or however many times is small, right? Is that going to change your row space at all? No, because I can always undo that, right? What's the third one?
Multiply by a constant.
Yeah, multiply by a constant and then add. Multiplying by a constant and then adding another vector is just a linear combination, isn't it, of the rows? What's your row space again? The span of the rows, or the set of linear combinations of the rows. So do elementary row operations affect your row space at all? No. So elementary row operations don't do anything to your row space, okay? So the answer to this is none. Okay? All right. So how would I find a basis for these 2 spaces? Okay? So a basis for your row space. Use the rows in the reduced row echelon form. Okay? Okay? So in this case, the basis for your row, and I'm going to write them horizontally only because my rows are written horizontally. I would use 1, 3, 0, 0, 1, negative 2. 0, 0, 1, 0, negative 1, 1, and 0, 0, 0, 1, 4, 2. Again, use the rows in the reduced row echelon form. Do not try to go back and pair them up with the original rows. Why? What was the first row operation you told me? Row swap. Do I know that if I use my calculator, do I know that I did a row swap? No. So I don't know if these 3 rows line up with those 3 rows when I'm done unless I do it by hand. Do you want to do it by hand? No. Okay? So I don't go back and pair it up to the original. Okay? Literally use the rows in the reduced row echelon form to find your basis for the row space. Okay? And again, that's because when you use your calculator or when you use a computer, you don't know if there were row swaps or not. I don't know if they match. Okay? Now, we can trick it into it, and we'll talk about how to do that. Okay? But for right now, if I just want to find a basis for the row space, I use the rows that are left. Basis for your null space, well, you already know how to do that. Let me scroll back up. Over here on the right, right here, over here on the right, that was our solutions, right? We talked about this a little bit before. Are these 3 vectors linearly independent? Yeah, notice what wherever I factored out this coefficient, this one was right here. What do I have in the other 2? Zeros, right? S, factored it out from here. The other 2 are zeros, and the same thing with the t. So those 3 vectors are your bases. Okay? So in this case, your basis is going to be, pardon, goodness gracious. Yes.
So when we also ready the rows, do we write it as a hyperpivot?
You're only going to pick the ones that have a pivot, because if it's a row of zeros, that wouldn't be linearly independent. Okay. So up here again, if I remember what the vectors are, we've got -3, -3, 1, 0, 0, 0, 0. And I'm just writing them horizontally. You can write them vertically if you like. It doesn't matter. What was the other one? It was, thank you. And the last one was, okay. That okay? Last thing I'll ask, and then we'll finish this off. Do elementary row operations change a column space? Remember, column space is the span of the columns, right? So let me start with this. If I row reduce this, I get that, don't I? Okay. Is the span of these two columns the same or different than the span of those two columns? And they're different, right? In particular, what can I never get in the second component when I do the span of this? What can I never get in the second component? Anything other than 0. Those are definitely different than 0, aren't they? So elementary row operations change the column space. So how do we go back and find the basis then? We already talked about this, right? Rather than just using the columns in the reduced row echelon form, what do? You go back and grab the columns in the original, don't we? Okay. So if I wanted a basis for looking at this example, if I wanted a basis for the column space, what columns are you interested in? 1, 3, and 4, right? So a basis for your column space here will be this is what I will write as columns because it says column space, but you can write them as rows if you like. I'll use 3, -9, 2, 6. We'll use 2, 4, -1, -1, and we'll use -7, -6, 1, -1. This is just like what we did before, right? Go back to the original matrix and pull out the columns with pivots, okay? Because why? If I do elementary row operations, do you ever do any column swaps when you do elementary row operations? No, columns don't change, right? So I know what they go back to the original to go pick them, match them up with. Okay. We'll finish this up on Wednesday, as well as get into some new stuff. Okay. Otherwise, have a good one. See you on Wednesday. Again, as you're going through your exam and reviewing, if you want to come by and chat about things, absolutely happy to do that. Just come by and see me.